After we determine process stability via control charts, we'll then determine if the process can consistently meet customer expectations via process capability. That's CPK. We'll also relate CPK to Six Sigma since both ideas are basically the same. Again, statistical process control, SPC, evaluates process variation, and control charts determine process stability. Is the process in control, like our teenage driver? If the process is not in control, we can apply Lean and/or Six Sigma to stabilize it. So once the process is in control, we then need to ensure that it will consistently meet customer expectations. That's customer specifications or customer specs. Recall our definition of quality: consistently meet customer value expectations. And this is where we check that. We statistically evaluate the quality of the process. The tool to do so is process capability, CPK. Will the process consistently produce within customer specifications? And if so, the process is considered capable, capable of consistently meeting customer expectations. And if it's not, we can again turn to Lean and/or Six Sigma. And we'd look for assignable cause and ideally address or eliminate issues before defects are produced. So SPC does not just measure quality, it's a proactive approach to reduce defects. Summarizing, control charts determine process stability. And here we're not yet necessarily concerned with customer expectations. We just need that process stability first. Then process capability will help determine if the process can consistently produce to customer expectations. Is the process capable of meeting customer specs? And here we're now directly concerned with customer expectations. And these customer specifications or specs represent some acceptable range of customer expectations, some acceptable variation. And these may come directly from customers or perhaps from our engineering or design department who translate the customer needs. So the specs represent the voice of the customer. For each metric, we likely have both a lower spec limit, the LSL, where anything below that is a defect, and an upper spec limit, the USL. Anything above that is a defect. So in between the lower and upper spec limits is acceptable, meaning not a defect, meaning customer allowable variation. Recall that we already had this discussion with our coffee temperature in the Six Sigma chapter. It's basically the same idea. CPK is the calculation for process capability. The only difference from Six Sigma is that CPK evaluates plus and minus 3 sigma process variation. Again, that sigma represents the standard deviation. CPK compares plus and minus 3 sigma of actual process variation to customer specifications, that allowable customer variation. If plus and minus 3 sigma of actual process variation falls within customer specs, then our process is capable of consistently producing within customer specs. Another way to say that is actual process variation will consistently fall within customer specs. The formula for CPK looks intimidating. However, we'll break it down. It's not that complex. And besides, you only need to interpret the results not calculate them for this class at least. And our target for CPK is at least 1.33. And yes, that does sound random, but will make sense after we visualize it. So if the CPK is less than 1.33, we would stop to fix the process via Lean and/or Six Sigma. Let's visualize our coffee example again. Remember that we had our lower spec limit, the LSL, at 130 degrees. Anything lower than that is a defect. Then we also had the upper spec limit, the USL, at 160 degrees. Anything above that is also a defect. So everything in between 130 and 160 is not a defect. That means it's customer allowable variation. CPK evaluates where the actual process variation falls relative to these spec limits. So let's consider a scenario of coffee temperatures that follow a normal distribution, but part of that distribution, specifically the upper part, falls beyond the upper spec limit of 160 degrees. In this scenario, the CPK calculation would be less than 1.33. And more specifically, it would be less than 1. The process is not capable of consistently producing within customer specs. Specifically, it will occasionally produce coffee that is too hot. Consider another scenario where the lower part of the distribution falls beyond the 130-degree lower spec limit. This process is also not capable of consistently producing within customer specs. The CPK is less than 1.33. It will occasionally produce coffee that is too cold. Then next, consider a highly variable process signified by a very wide distribution of temperatures. Both sides fall beyond spec limits. That is, the lower end of the distribution falls beyond the lower spec limit, and the higher end of the distribution falls beyond the upper spec limit. Again, the CPK would be less than 1.33. The process is not capable of consistently producing within customer specs. It will occasionally produce coffee that is too cold as well as too hot. Now consider a scenario where -3 sigma actual process variation falls right on the lower spec limit. And then +3 sigma actual process variation falls right on the upper spec limit. So in other words, plus and minus 3 sigma actual process variation fall right on the spec limits. In this case, the CPK would be exactly 1. The process is technically capable of consistently producing within customer specs, but it's right on the lines though. We'd actually prefer some cushion, meaning a bit more certainty. That's why we target a CPK of 1.33 for the extra cushion. Finally, consider a scenario where plus and minus 3 sigma of actual process variation fall well within the spec limits, including the lower spec limit and the upper spec limit. So we have some cushion on both sides. In this case, the CPK would likely be greater than 1.33. The extra 0.33 is the cushion of extra certainty. So this process is capable of consistently producing within customer specs. Let's return to our medical appointment time example that we discussed earlier in the chapter. The expected duration of each appointment is 25 minutes. Nevertheless, actual appointment times will vary, at least to some extent. And based on detailed feedback from customers, the patients, we've determined that they want appointments to last at least 15 minutes. That's the lower spec limit. Otherwise, they feel that they were rushed and didn't get sufficient care. However, they also don't want their appointments to last more than 35 minutes. So that's the upper spec limit. Otherwise, they feel that some of their time was wasted. Let's evaluate the process. So we take a large sample of appointment duration times and find a sample mean of 30 minutes and a standard deviation of 2 minutes. That mean of 30 minutes falls within specs, but what about the entire distribution? The CPK formula will show us. So if we break it down, the first part of the formula evaluates how close -3 sigma, the lower part of the distribution, is to the lower spec limit, the LSL. And the second part of the formula evaluates how close +3 sigma, the upper part of the distribution, is to the upper spec limit, the USL. And higher values are better, lower values are worse. So the CPK formula considers the minimum, the lower or the worst of the two evaluations of the lower spec limit and the upper spec limit. It takes the lower of the two numbers. In our example, the calculation for the lower spec is 2.50, which is greater than the target of 1.33, which is good. But the calculation for the upper spec limit is 0.83, which is less than the target of 1.33, so that's bad. Then the worst case, the minimum of the two numbers is 0.83. So the CPK is 0.83, which is less than the 1.33 target. So this process is not capable of consistently producing within customer specs. Specifically, the upper CPK is problematic. That means appointments will occasionally last more than 35 minutes, that upper spec limit. We can visualize this with our lower spec limit, which is 15 minutes. Anything less is a defect. It's too short. And then our upper spec limit is 35 minutes. Anything longer than that is a defect, too long. So everything in between 15 and 35 minutes is within specifications. That's customer allowable variation, and it's not a defect. So this particular distribution mostly, but not completely, falls within specs. The lower part of the distribution is well within the lower spec limit, plenty of cushion, and the lower CPK result shows this with 2.50, which is greater than 1.33. But a portion of the upper part of the distribution extends beyond the upper spec limit. So some appointments will last longer than the 35-minute upper spec limit. And the upper CPK result shows this with 0.83, which is less than 1.33. So this process is not capable of consistently producing within customer specs. Okay, so let's apply some lean, including Tim Woods, to fix it. Specifically, we notice that the actual average of 30 minutes is a bit too long. So we conduct a Kaizen blitz and we knock the mean down to 25 minutes. And that will shift the process down to the middle of customer specs. With the new mean, the lower CPK is 1.67, which is still good. We've lost some cushion relative to the lower spec limit, but we're still greater than the 1.33 target. The upper CPK is also 1.67. Do it again. We now have a bit of cushion relative to the upper spec limit and are greater than the 1.33 target. The process is capable. We reduced the mean, we centered it, shifting that distribution so that it's now capable. Let's suppose that instead our Kaizen blitz doesn't shift the mean, but rather it reduces the variation of the process. And that will narrow the distribution. So the previous standard deviation was 2, and our Kaizen blitz reduced it to 1. The lower CPK is now 5, which is even better than it was before, and we've gained some cushion relative to the lower spec limit. So we're still very much greater than the 1.33 target there. The upper CPK is now 1.67, which is also good. We have a bit of cushion relative to the upper spec limit and are again greater than the 1.33 target. This process is capable. So either reducing the mean or reducing the variance, or perhaps both, will get a process within specs, a capable process that will consistently meet customer expectations. Recapping, control charts evaluate process stability with control limits, the upper and lower control limit. Is the process stable? Process capability, CPK, evaluates if the process can consistently meet customer specifications with spec limits, the upper and lower spec limits. Is the process capable of consistently meeting customer specs? Note the specific wording of stability with control charts versus capability with CPK. So we should first make sure that the process is stable via control charts before evaluating process capability via CPK. That is, process stability is a necessary condition for process capability. A process that is not stable will likely not be able to consistently meet customer expectations. Let's wrap up the section by relating Six Sigma to process capability, CPK. They both evaluate if a process can meet customer expectations. And recall that Six Sigma focuses on reducing the variability of a process. Less variability means more consistency. And the DPMO chart shows the quality performance of different levels of sigma. And a 3 sigma process is equivalent to a CPK value of 1. Such a process has relatively decent quality with about 6.68% defects, but a 6 sigma process has virtually no defects, virtual perfection. And as we'll see next, a 6 sigma process is equivalent to a CPK value of 2. That is, it doubles a 3 sigma process. Again, both Six Sigma and CPK assess actual process variation relative to customer allowable variation. That means customer specs. So they're directly related. If we know one, such as the sigma, we know the other, the CPK, and vice versa. In other words, to determine the sigma of a process, you can calculate the DPMO, defects per million opportunities, or you can calculate the process capability, CPK. It's the same answer. Picture again customer specifications. We have the lower spec limit, Anything below that is a defect. And also the upper spec limit, anything above that is also a defect. Then, as we've seen, everything in between is acceptable variation, customer allowable variation, not a defect. So let's consider different actual process distributions, meaning actual process variation. For instance, a distribution that is inside spec limits, let's say it has a CPK value of 1.33, and we see a bit of cushion between the -3 sigma and the lower spec limit. And in fact, the -4 sigma of actual process variation crosses the lower spec limit. And we also see a bit of cushion between +3 sigma and the upper spec limit. +4 sigma of actual process variation crosses the upper spec limit. This CPK value is 1.33, and it's a 4 sigma process. So CPK of 1.33 is a 4 sigma process, and the process is capable. A distribution that is right on the spec limits has a CPK value of exactly 1. There's no cushion between -3 sigma and the lower spec limit. That is, -3 sigma of actual process variation crosses the lower spec limit. And there's no cushion between +3 sigma and the upper spec limit. That is, +3 sigma of actual process variation crosses the upper spec limit. So this has a CPK value of 1, which is equivalent to a 3 sigma process. Recall that we set the CPK target of 1.33 for some cushion, for some extra certainty. So this CPK value of 1 is barely capable. We prefer some cushion, so our CPK target is 1.33. A distribution that extends beyond spec limits, say with a CPK value of 0.67, we see -2 sigma of actual process variation crossing the lower spec limit and +2 sigma of actual process variation crossing the upper spec limit. The CPK of 0.67 is equivalent to a 2 sigma process. The process is not capable. It will occasionally produce outside of customer specs, meaning occasional defects. A distribution that is well within spec limits with a CPK value of 2, we see -6 sigma of actual process variation crosses the lower spec limit, and +6 sigma of actual process variation crosses the upper spec limit. So a CPK of 2 is equivalent to a 6 sigma process. The process is extremely capable of consistently producing within customer specs. It will almost never produce outside of customer specs, meaning virtually 0 defects. So a CPK of 2 means that a process has achieved 6 sigma. Again, CPK of 2 means 6 sigma quality. And it makes sense. CPK divides by 3 sigma, so doubling it means it's equivalent to 6 sigma. Again, to determine the sigma of a process, you can calculate the DPMO, defects per million opportunities, or calculate the process capability. It's all the same answer. One more time. Consider the actual variation of a process. Every process has variation to some extent. And then we compare that to variation allowed by the customer, meaning customer specs. A 6 sigma process means that plus and minus Six Sigma of actual process variation fall within customer specs. Virtually all of the actual process variation falls within customer specifications. Six Sigma quality means 3.4 defects or fewer per million opportunities, which is virtually perfect. Suppose that our restaurant is concerned about how long customers wait to receive their food after ordering. In rigorously working with our customers, we determine that anything faster than 10 minutes is too fast. The customers feel rushed. So that's the lower spec limit. And then anything longer than 20 minutes, well, that's too slow. Customers feel ignored, and then the food may not be hot or fresh. So that's the upper spec limit. The customer specs allowable variation are 10 to 20 minutes of waiting time. Then if we measure all the orders, or as many as we can, and 99.99966% of all meals are served between 10 and 20 minutes, we've achieved a Six Sigma level of quality. The wait process is virtually defect free. The wait time will almost never be shorter than 10 minutes or longer than 20 minutes.